Hello, this is an Algebra 2 video. It is Chapter 8, Section 4, and we're going to continue in the graphing. We were graphing reciprocal functions in the last section, and so in this section we're going to graduate a little bit to graphing rational functions. And the basic difference between what we were doing in 8.3 and what we're doing in 8.4 is that in 8.3, the numerator of your function was a 1, or it was another constant. But in this case, for a rational function, it's kind of like a reciprocal function, where on the bottom you do have a polynomial of sorts. But that polynomial doesn't have to be linear like it was in the previous lesson. And also you have a polynomial on the top. So basically this is what it looks like. You have f of x equals a of x over b of x, where a of x and b of x are both polynomial functions. It could be x squared, x cubed, whatever. And also, of course, b of x cannot equal 0, because if it did, then you would have division by 0. And that brings us to our next part of a rational function, the vertical asymptotes. Because the bottom can't equal 0, you can find your vertical asymptotes for a rational function always by setting the bottom of the function equal to 0. And whatever values you get for that, those are going to be your vertical asymptotes. But for your horizontal asymptotes, you actually have 3 different possibilities, and technically 4, but we'll get to that technicality later on in the lesson. So for the horizontal asymptotes, I'm going to put up here a function, and I want you to just kind of understand that I'm only basing this off of the leading term of the function. So on the top you have a is just a coefficient, and then x to the nth power, and this dot 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 means that the polynomial can keep going. But I'm not really interested in everything that comes after. I'm just interested in the beginning, the leading term, provided that it is in standard form, meaning that the leading term would be the biggest exponent. On the bottom, same thing, only b now the coefficient of x to the nth power. And so the 3 scenarios are based on the exponent m and n. That's why it's important for you to know what those are. So the first option is when the degree or the exponent on the top of the rational function is larger or greater than the degree of the exponent on the bottom. When that happens, you don't have an asymptote. There is no horizontal asymptote when the degree of the top is bigger than the degree of the bottom. In option 2, that would be the opposite, or the reverse of that. If the degree on top is smaller than the degree on the bottom, then the asymptote will be y equals 0. Y equals 0 is basically the x-axis. So I can add that to this here. Okay. My pen's got all crazy on me. Okay. So basically, we have here the x-axis is your horizontal asymptote. And then the last scenario is when the exponent on the top and the exponent on the bottom are the same. What happens if m equals n? In that case, your horizontal asymptote is going to be the ratio of the coefficients. So a and b. Now a is the coefficient on the top, b the coefficient on the bottom. So if the coefficient on the top was 2, and the coefficient on the bottom was 4, then the answer would be y equals 2 over 4, basically y equals 1/2, and you would literally have a horizontal line that goes through 1/2 on the y-axis as your horizontal asymptote. So those are the 3 scenarios for your horizontal asymptotes, your vertical asymptotes for rational functions, and we're going to get right into it and graph. When you are graphing a rational function, you want to keep in mind these 3 things as far as what you need to do. You need to find any x or y intercepts. You need to find the asymptotes, both vertical and horizontal. And then you want to graph or make a t-table. And you want to make a t-table that uses the x and y intercepts and the horizontal asymptotes. And you want to make sure that you have points in between and beyond those values. So I'll show you what I mean. The first thing we want to do is find an x or y intercept. To find the x-intercept, you basically make y equals 0. Okay, so in this case, if you make y equals 0, you're going to get this little guy. Now we can all agree that the bottom of the fraction is going to be where we're going to find our vertical asymptotes. When you're finding the x-intercept for a rational function, then you don't need to include the bottom of the function when you're finding it. This is sufficient. 0 equals x cubed. So whenever you want to find the x-intercept, you can do so by making the top of the fraction equal to 0, and that'll give you the x-intercept. In this case, because it's 0 equals x cubed, we're going to get that x equals 0 as well. The only time that x cubed will equal 0 is if x is 0 to begin with, which basically tells you that your x-intercept and your y-intercept are both 0. So we know we're going to have a point over here at 0, 0. There we go. All right, so that's going to give me my zeros. The next thing you want to do is move on to your asymptotes. For your vertical asymptotes, you want to take any time the bottom of the equation is going to equal 0. So for your vertical asymptotes, you want to take the bottom and make it equal 0. And in this case, if I add 1 to both sides, x equals 1 is my vertical asymptote. Your horizontal asymptote, because the top is a 3x cubed and the bottom is x to the 1, since 3 is larger than 1, I have no vertical asymptote. If you recall, if the top is bigger than the bottom, then you have none. Okay, so I have 1 as my vertical asymptote, I have no horizontal asymptote, and I have 0, 0 as my x and y intercept. So then the next thing you want to do is your t-table. And so in your t-table, you want to make sure that you have 0, 0, which is your x or y, in this case the same intercept. You want to make sure you put your vertical asymptote, even though we know that the value there is undefined. We can put undefined like that. Okay, we know that there is no value there. It's an asymptote. That means that there's going to be an imaginary line going through x equals 1. And we can actually go ahead. We're going by 2's here, or 1, 2, 3. So we're going to put this line in here. Might as well get going here. Okay, so there's your asymptote. So we know that there's actually no value there for the y, but we can just put 1 undefined. And then we have no horizontal asymptote. And so basically what you need to do once you've done that is to pick points that are beyond okay. Seriously, this thing is driving me nuts. Okay, so, sorry about that, my pen is getting kind of weird here. So we're going to have -1, -2, so these values are beyond the 0, but you also want to pick numbers between 0 and 1, so there's not much between 0 and 1 other than a fraction, so maybe we'll pick 0.5, and the numbers beyond 1, like 2 or 3, okay? And then you want to go to your calculator and basically plug in those values. So, for -2, we're going to get approximately 2.67. For -1, we're going to get 0.5. And this is just in the interest of time, but you basically need to plug in these x values to get that. When x is 0.5, we get y is -0.25. And when x is 2, you get 8. And when x is 3, you get 13.5. So then you just take those values, and now you can go ahead and plug them into your graph over here. So we have -2 is here, and it's almost at +3. So we're going by 2's here, so it's 2, 4, so it's somewhere in here. -1 is going to be 0.5, so this is 1, 2, so we're going to have 1/2 is right about there. And then we have 0, 0 already. And then when x is 1/2, you have 0.25 right about there. And then it's undefined. So this part of the graph is going to look like this. okay? Remember, it can't cross the asymptote, so it's kind of just going to be really close to it, but not going to cross it. And then at 2, you're going to have 8, 2, 4, 6, 8. Who do we appreciate? 3 is going to be 13 and a half, so it's going to be up here somewhere. But you can basically see, you can also check with your calculator to kind of see if you're onto the right track. And so I'm going to confirm kind of like that graph you have going on. And again, you can always plug it into the calculator afterwards to make sure that you have the right graph to give you an idea. But that does not mean that you don't have to have your work shown for all of these parts. I want to see that you're finding your x and y intercepts. I want to see that you're finding your vertical and horizontal asymptotes. And I definitely want to see your t-table. And then you can use the graphing calculator to help you put it all together. But I definitely want to see this work, otherwise you're not going to get full credit. So now you can try this do-it-yourself question, and here's part A. And I wanted you to have enough space, so here's part B. Now we're going to go to example 2. It says a boat traveled upstream at r sub 1 miles per hour. During the return trip to its original starting point, the boat traveled at r sub 2 miles per hour. The average speed for the entire trip, r, is given by the formula capital R equals 2 times little r sub 1, little r sub 2, divided by little r sub 1 plus little r sub 2. So, it says in part A, let little r sub 1 be the independent variable. Basically, that means that treat little r sub 1 like if it was x. And let capital R be the dependent variable, which basically means treat capital R like if it was y. Draw the graph if r sub 2 equals 10. That means that they want you to replace this little guy with a 10. So 10 times 2 is 20. And then on the bottom, they want you to also replace this little r2 with a 10. So you're going to get r sub 1 plus 10. And so there's still an r sub 1 there. So 2 times r2 is going to be 20, but the little r1 is still there. And so they basically want you to graph this guy right here. I'm not actually going to graph it in the interest of time, but you saw earlier how we do that graph, so that's kind of what you're graphing now is 20 r sub 1 over r sub 1 plus 10. Remember that the r sub 1 is kind of like your x variable, so if you want to just write 20x over x plus 10, that's fine. It says, what is the r-intercept of the graph? Remember to find the r-intercept, basically that they want the y-intercept, means that you make x equals 0. So if I were to take and put a 0 in the place of the variable here, I would get 20 times 0, which is 0, divided by 10, which is still 0. So the r-intercept of the graph is 0. So I want to write that in there. 0, 0 is going to be your r-intercept for your graph. And then part C says, what domain and range values are meaningful in the context of the problem? You can actually see what the graph of this looks like on page 555 in your textbook. But basically, because you have the variable here has the same exponent. This is r sub 1 to the 1 power, r sub 1 to the 1 power. Because the exponents are the same, that means that the horizontal asymptote is going to be the ratio of the coefficients, the ratio of 20 divided by 1, or basically 20. That means this graph is going to have a horizontal asymptote of 20. So if you were going to graph it very loosely, you're going to have a horizontal asymptote at 20. This is 20. And then, of course, it says what values are meaningful. Let's see here. This is 20. It wants to know what domain and range values are meaningful. For domain and range, you definitely want it to stay in the positive. If you have negative values, that's going to be negative speed. Doesn't make any sense. So you definitely want to stay in the top quadrant here. So definitely want to be greater than 0, but also you want to be below this 20. Because if you actually saw the graph of this function, it looks something like this, where you have negative 10 becomes a vertical asymptote. So you also have a vertical asymptote, kind of like right there. And when you graph this little guy, he's going to look something like this and like this. All right? And so you can see that we don't care about anything that's over here in the negative region, and we definitely don't want this function to go beyond over here either. So we want it to stay in the positive, but we also want it to stay below 20 because of this asymptote. So what values are meaningful in the context of this problem? Well, you want it to be for the little r1, we'll start with that little guy right there. For little r1, you want it to be greater than or equal to 0. And then for r, big R, which is the y values, you want those to be also between 0 and 20. Okay, so the domain is a little r1, greater than or equal to 0. For the range, you want it to be less than 20, but greater than or equal to 0. So there you go. So now you can try this little guy on your own, and then we're going to go to the situation I was talking to you about earlier, which is not technically a horizontal asymptote, but it's an oblique, or what we usually call a slant asymptote. And you have a slant asymptote, which is basically when you get a graph and the asymptote is not horizontal, it's not vertical, it's at a diagonal, it's at a slant. And it looks something like this. And I just want to show you kind of what that would look like if you had an x and a y axis, something like this. Sometimes you can have a slant asymptote where the graph will kind of be like this. So it has this asymptote happening along this diagonal line here. So we're going to talk about how does that happen, when does that happen, and then how do we graph something like that. So that's example 3 here. So I'm going to show you right now how to do that. First of all, it only happens when the degrees, the difference between the 2 degrees here is equal to 1. So the degree on top, the 2, is bigger than the degree on bottom. So normally we would say it doesn't have 1, with the exception of when they equal 1. Their difference is equal to 1. So in this case, the m value is 2, the n value, is x to the 1 power, is 1, and 2 minus 1 equals 1, which is the one case where you would get an oblique asymptote. So how do we find the oblique asymptote? That's the question. While you do that, it looks like it has the answer right here, but this might make no sense to you. You're probably going, what in the world? This is basically division. It's long division. You take the polynomial on the top and divide it by the polynomial on the bottom with no remainder. So what does that mean? It means that you go back to long division, and I'm going to say 2x minus 1 goes into x squared plus 4x plus 4, but I'm going to ignore the remainder. So this will give you a little refresher of how to do long division if you have forgotten. But we need a 2 and an x here, because 2x times, I'm sorry, I don't need the 2 there. I just need a fraction here. So if you remember how to do this, I guess I'll tell you. If you don't know what to put up there, you always take the ratio of the leading term of the numerator, so that's x squared, divided by the leading term of the bottom, which is the denominator, so 2x. So x squared over 2x. What's going to happen when you have x squared over 2x is that the x on the bottom is going to cancel with one of the x's on top. So you're going to end up with 1/2 x. That's actually what needs to go right here, 1/2 x. So when you go 1/2 times 2, you're going to get 1. X times x is x squared, and you're going to get 1x squared. 1/2 times -1 is -1/2 x. Then you subtract. So x squared minus x squared is 0. They cancel. 4 minus -1/2 is actually 4 plus 1/2. So now 4.5, which is basically 9/2, and then plus 4. Alrighty then. Waiting on my pen. Okay, there it goes. All right, so then again, if you want to know what to put on the top, you take your 9/2 x and divide it by the 2x. And when you do that, your x's are going to cancel. And then 9/2 divided by 2 is the same thing as 9/2 times 1/2, which is basically 9/4. So 9/4 is what goes up here. Okay, so 9/4 times 2 is going to give you 9/2 x. And then 9/4 times -1 is -9/4. Subtract 9/2 x minus 9/2 x is going to cancel. 4 minus negative is actually 4 plus, so you're going to get 4 and 9/4. 4 and 9/4. But at this point, you can't go any further with the division, and it doesn't really matter what 4 9/4 is, because it says up here that you do the long division, but with no remainder. So this is the remainder, and we don't actually have to simplify the remainder because we don't care about the remainder. We only care about the equation that is left up here. Oops, did not want to do that. This little guy right here, that becomes your oblique asymptote. 1/2 x plus 9/4 is your oblique asymptote. So what about your vertical asymptote? So we have no horizontal asymptote, but for your vertical asymptote, that still happens the same way as it normally does. You take 2x minus 1 equals 0, and so x is going to equal, add 1, divided by 2, 1/2. So your vertical asymptote is x equals 1/2, so I'm going by 2's here, 2, 4, 6, 8. So this is going to be 1, 1/2 is going to be really tight here, but I'll try to put it in there so you can see, just like that. If my pen would cooperate with me, it'd be lovely. Yay, okay. So there's your 1/2 approximately for your vertical asymptote. Your oblique asymptote is going to be 1/2 x plus 9/4. So you guys know how to graph y equals mx plus b. The y-intercept is 9/4, and 4 goes into 9 twice, with the remainder of 1/4 left. So we're going to be right about 2. So something like right here is your y-intercept, and the slope is going to be up 1 over 2. So it's going to be up 1 over 2, right there. So it's basically going to be like this. Okay, so you're graphing the slant or oblique asymptote like you would a normal linear function, with the y-intercept being 2 and 1/4, and then I'm going up 1 and over 2 approximately, and that's how you get your oblique asymptote. And then you're going to graph the rest of it just the way we did in the previous lesson. Again, in the interest of time, I'm not going to go through all those steps right now. I thought it was pretty important that you see how to get the slant asymptote in the first place. But at that point, you can actually use your calculator. You're going to get 2 branches of your graph going like this. And we definitely don't want them to be dashed because it should be solid. Solid as a rock. You're going to have your graph do something like this. But again, you can get those values by picking values for x that are before 1/2 and after 1/2, and then you'll be able to fill in the rest of your graph there. So I hope that you understood how to find the oblique asymptote. You basically do long division and ignore the remainder, and this equation, it's going to be linear. It has to be linear, otherwise it wouldn't be a line. And so that will be your oblique asymptote, and then you graph it like you would y equals mx plus b. Okay, so now we want you to try the next 2, and this is part A, and this is part B, and then we're going to go to our last example for today, and that's what happens when you have a graph that is point discontinuity. And what point discontinuity refers to is when both the numerator and denominator have a common factor. So a of x and b of x have a common factor. So when that happens, We call it a removable discontinuity. And you might look at this and think, oh, it's going to have a vertical asymptote at 4. But it actually won't have an asymptote at 4. It's going to have a gap at 4. And I'll show you how that happens. The first thing you want to do is definitely factor, because the top is a difference of 2 squares, x squared minus 4 squared. You're going to get x minus 4 on top and x plus 4 on top. And on the bottom you have the x minus 4. And so now it might seem clear to you that the x minus 4 factor is going to cancel, and all you're going to be left with is x plus 4, which is actually not even a rational function at all. We could graph x plus 4 very easily. It's linear, and so the y-intercept is 4. So over here we have 2, 4. And so then you're going to have your slope is 1. So if I go up 2, I go over 2. That's the same thing as 1. Down 2, over 2, same thing as 1. And so we're going to have our line. It's going to look something like this. But what's going to happen is that when x is 4, there's actually not going to be a value there. We're just going to draw in an open circle to indicate that that value doesn't exist. Because even though we factored out the x minus 4, that's why we call it a removable discontinuity. It's still going to be a discontinuity. The function is still going to be discontinuous there, but you can remove it. And so when you can remove it, you don't have an asymptote anymore. So you only have an asymptote when the bottom doesn't cancel with the top, and then you have to make the bottom equal to 0. But in this case, the bottom canceled, and so that asymptote is not even present anymore. Instead, you have basically a gap in the graph. So you end up with f of x equals x plus 4. So this function and the original function are pretty much the exact same function, with the exception of the point 4. That's why it's called point discontinuity. All right? So I'm going to let you do this little guy, part A. Remember, factor the top, and then you can see that it will cancel with the bottom. And this one as well, and I will give you a hint for the top. You want to factor the top by grouping, and if you do that, you'll see that you will get some nice point discontinuities. All right, so that is how you do that. So once you have completed this example, you will have completed your notes for this lesson, and I will see you in class, and thanks for watching.